constant acceleration motion. We've talked before about motion that has a constant velocity. So when you're traveling at a constant velocity, your velocity is unchanging. So every second you're covering the same distance or displacement. Acceleration is the rate of change of velocity. And there is an equation there, delta V over delta T, rate of change of velocity. Now, acceleration is a vector. And I just want to point out here a kind of nifty thing about acceleration is that if your acceleration is negative, it doesn't necessarily mean you're slowing down. The negative, when we're talking about straight line motion, just indicates the direction that that acceleration is pointing. And so, because it's a vector, if your velocity is in the positive direction, whichever direction you define as positive, and then you have a negative acceleration, that does mean you're slowing down because your acceleration is pointing in the opposite direction to your motion. However, if you have a negative velocity, which means you're pointing or you're traveling in the negative direction, and you also have a negative acceleration, what do you think that means? It means you're speeding up. It just means you're speeding up in the negative direction. So that's just something to keep in mind when we're dealing with acceleration. And just to give you, if you still don't have a really good picture in your mind about what acceleration is, just say we had an acceleration of 10 meters per second squared, because meters per second squared are the units. What that means is that every second, the speed is changing by 10 meters per second. And if we go and have a look up here, every second down here, the speed is changing by some amount. So I'm just going to write that down. Okay, so there's just some little introductory hints of dealing with acceleration. I'm going to draw a motion map of the motion of a cart moving just in a straight line. And so here's our cart here. Again, I make the same joke. I bet you're glad I'm a physics teacher and not an art teacher. And that cart is moving in the positive direction. So it's moving towards the positive numbers on that line. Okay, so at the initial time point, it's at -8, then it's at -3, then it's at 1, and so on and so on and so on. Just draw some arrows in there to show that it's moving from one to the other. And I've just plonked on there some axes. You'll have a look here. You can see that this is displacement versus time. This is velocity versus time. And this is acceleration versus time. And I haven't really drawn the scale on these axes. They're just supposed to give you the general idea of what that motion will look like. So you can see here, just by looking at this motion map, that every unit of time, that motion is traveling, or that cart is traveling a smaller distance. Okay, so it's obviously quite fast at the beginning, then it's getting slower and slower and slower and slower. All right, so let's plot the distance or the displacement of that cart as a function of time. There we go, over time, it's moving a little bit less distance. So that is our displacement versus time. What is our velocity doing as a function of time? Well, it's getting less, isn't it? It starts off fast, then it's getting less and less and less and less. Okay, so in that last time unit, it's just moved 1 meter or 1 centimeter, whatever that unit is there, I haven't specified. So if we think about what acceleration means, it means, and how we need to draw that, how we can interpret it from that graph. Acceleration is how much the velocity is changing every unit of time. So we can look at that and say, well, the velocity is getting less every unit of time. Acceleration must be negative, which we can interpret from knowing that the car is traveling in a positive direction. So that acceleration vector is pointing in the opposite direction to the motion of that cart. And assuming we've drawn this correctly, our velocity graph here suggests that for each unit of time, that velocity is changing by the same amount. Okay, so the change in velocity every unit of time is the same, which suggests that the acceleration is constant, as well as being in a negative direction. So let's draw that. Okay, I haven't put any units on there, I haven't shown the scale, so we're just doing it in a kind of qualitative way. Okay, so I'm just going to draw some trend lines in there to just show those trends a little more easily. So there's our displacement. We're assuming we've got a straight line decreasing in value for the velocity, and our acceleration is constant. So now I'm going to show you some key points, key summary points for interpreting graphs of motion for constant acceleration motion. All right, so here are our key points. The first key point is that the slope of your displacement time graph gives you the velocity. And if your displacement time graph is a curve like we have here, then the slope at any point, so the tangent to that line, gives you the instantaneous velocity, the velocity at that particular point in time, like on your speedo on your car. The next interesting point is that if you worked out the area under a velocity time graph, you would get the total displacement that's been travelled. And so if I worked out what in the first 2 time points there, what the area under that graph was, I could actually work out what the total displacement that had been travelled would have been, so between the beginning of that motion and the end. We'll do some examples of these in class. And I'll just add in here a little slope on that displacement time graph there to show that it's the slope equals the velocity at that particular point in time. Okay, the next key point is that the slope of the velocity time graph gives the acceleration at that particular point in time. And we can look at the slope there. You can see over the velocity time graph there, just drawn in green. We take the slope of that, rise over run, that gives us the acceleration at that point in time. And the last key point is that the area under the acceleration time graph gives us the change in velocity. And again, just work out that area, and it's the change in velocity for that time period there. There's another video included in the list which goes through using some of these and talks about these relationships in a bit more detail and shows how we can derive the equations of motion, or the kinematic equations, from just looking at the graphs and the relationships between those different variables.